All right, so let's go ahead and get started. So first, any questions about what we talked about yesterday or anything? Great. We didn't cover a ton of super difficult stuff yesterday, I think. So it was just more. I think the hardest part about yesterday was just the control structures in Bash scripts and like their syntax and everything. So if nobody has any questions, then first we will talk about second assignment, which I posted last night, and I made a post on Piazza about it. I changed a few things. I didn't change any problems or anything. I just changed some typos and stuff that some of the problems had, and this should be the final version though. So it's going to be due again this Sunday night by midnight Mountain Standard Time. And in this assignment, you'll be doing one Bash script that's going to involve using those control structures we talked about yesterday. And then there will be several C problems. There's 4 fairly simple C programs, and then one that's a bit longer. Again, a lot of people seem to have an issue with this line right here, but for each problem, you'll be turning in one file. So there's 6 problems on this assignment, so for each problem you'll be turning in one file, so you'll be turning in 6 files. Just turn in the individual files. Do not make a directory and put all of them in there. Just turn in each file individually, and whatever that problem is called, that's the name of the file you'll be turning in. That's a typo. That's missing a name. So for instance, this first problem, I just added the name. It's called todo.sh. You'll be turning in a file called todo.sh. For the C problems, this one's called rev_input.c. You'll be turning in a file called that. So if you're listening in online, make sure to do that when you turn in next time, because a lot of people turned in directories with their files for the first assignment, and we went ahead and moved them over. But in the future, if you do not do that, you'll get a 0, because we're not going to go through and fix your directory structure when we told you how to turn it in. Yeah.
You did a star when you turn in.
Yeah. So if you're in your directory and you have all your files in there and you just say turn in star, that's fine. But don't just say turn in directory name, because that'll mess up our grading script. So.
Would you turn in star with like the compiled Java files? Will that be an issue, or will it?
No.
Okay.
Our script will only look at the actual Java files, so that should be fine.
Extra files don't.
Extra files don't matter. Yep. Cool. Then we have a note and a restriction right here. So for all the C problems, or for problems 2 through 5, you cannot use any pointers, arrays, or memory allocation tools. So basically, you'll just be using function calls, simple I/O calls, and just arithmetic and things like that. For the 6th problem, you may use one integer array. We'll talk about arrays hopefully on Thursday, but they're not super difficult as far as that problem is concerned. The only library routines that you may use are getchar, scanf, putchar, and printf, and violating any of these restrictions will result on a 0 for that problem. So this first problem is called todo.sh, and it's basically just a simple to-do list. Brian's very familiar with this problem, and what it does is you'll have a file called todo.txt that maintains a list of tasks that you have to do. It's just a to-do list. So there's a few things here. If an invalid mode is specified on the command line, you should print the message unknown mode. If the database file or the todo.txt file does not exist in your current directory, when you try and run the script, you should say the to-do list database file is missing and exit from the script. So there's 4 modes, or there's 5 modes actually. There's list mode, which essentially just prints out all the things that you have to do on your to-do list. So this should be fairly simple because it should just be essentially printing out that file. But note how these all have a star in front of them. They won't have that star in the actual file. Second mode is called add mode, and you'll run it by just running the script and saying add, and there'll be 2 command line arguments, and the second one will be whatever task you want to add to your list. And once you successfully add it, it will just say to do entry, whatever you wanted to add was added. And that file that contains all the tasks will be updated. The next mode is remove mode, which will take 2 command line arguments, as shows right here. So you'll just run the script, and the first argument will be remove, and the second one will be a number, and that will just be whatever entry that you want removed from your list. So if we say remove 3 right here, and up here was our list beforehand, it should remove that entry that said be awesome. And then we remove it, and the next time we print it out, it's gone. And the final mode that you should have is clear mode, which just removes all entries from your to-do list. You would just say to-do.sh with clear as the command line argument, and it will remove all the entries from the file. So any questions about that? How that should work? Cool. Alright, the next one is called paren.c. So this program will determine if nested parentheses that exist are balanced. So this problem is not necessarily hard to actually program, but just thinking about how to do it might be tricky, but once you get it, you'll just be like, oh, that's really easy, and hopefully it'll be a really quick solution for you. But essentially how it works is you see it'll read some stream of characters on standard input, and it will either report that the parentheses are balanced or the parentheses are not balanced, as we see down here. Because here we have 3 open parentheses and only 2 closed. But up here, for every open parentheses we have, there's one that closes it off, so it is balanced. And the input may consist of any type of character, it won't just be parentheses, so if you get something that's not parentheses, you can just ignore it though. The next one is called revinput.c. This will read input on standard in. Essentially what this will do, it will print whatever input it is given in reverse. So you must use getChar to read the input for this problem, so you'll just be reading one character at a time. And then there's a hint right here. Try and use recursion for this one and the next problem. It'll probably help you out a lot. This next one goes along with rev input. It's essentially the same thing, except you're only reversing line by line. So this is like the rev command that you guys might have used on the first assignment for some of your scripts. As you see here, for rev line, it's given these lines of input, and then what line it's at stays the same, but it's just printed out in reverse, as opposed to rev input, which just completely reverses the input as we see up here. Any questions on those two? Cool. The next program is called rectangle.c. This will just be taking in pairs of integers. So the program will always read at least one pair of integers in. It might read more, but you just have to be able to handle at least 1 to n pairs of integers read in. And when it reads in that pair of integers, it'll print out a rectangle that is that size. And the rectangle will be made out of asterisks. So you will also print out the dimensions of the rectangle in the bottom left corner. So here we can see we run the program, we take in a 10 and we take in a 4. So that tells us that the rectangle would be 10 asterisks in width and 4 high. So then we print out the rectangle right here, and the dimensions are in the corner. You will never get dimensions that your dimension printout in the corner won't fit into. So right here, this is like the smallest rectangle that you could get. So you're given 7, 3, that's using up all the space within the rectangle. So a rectangle will never be smaller than that, because then it would look weird and you couldn't fit the dimensions into there. And then again, like I said earlier, you can take multiple pairs of integers in for every time you run it. So this is taking 2 pairs of integers in here. Yeah, this problem should be fairly straightforward in terms of what it's doing. Does this make sense to everybody? Great. The final one, this problem will be a little bit more difficult. It's called rpn.c. You'll be writing a reverse Polish notation calculator, and it will be stack based. So essentially what this will do is it has 4 operations: add, subtract, divide, or multiply, and it'll take input and it will read numbers in, and as it reads those numbers in, it will push them onto your stack. If you ever read in an operation, you will pop the 2 elements off the top of the stack, perform whatever operation was read in, and then you will push that resulting number back onto the stack. So again, we can just look at the input down here so you can see what I'm actually talking about. The input will consist of characters and numbers. So if you read in an n, that means the program's about to read in a number. So if you read an n, the next thing in input will be a number, and then you would read that number in and put it on your stack. If you ever read an a in, that means to perform an add operation. S means subtract, D means divide, and M means multiply. Is everybody with me so far? Cool. So for every character you'll read in, you'll want to use scanf, %c, and notice this new line character right here. You'll probably get weird behavior if you don't have that in both of these. So say scanf %c new line to read in each character, and then if you ever read in an n, remember the next thing you read in will be an integer, so then you can use the scanf %d to read in an integer, and we'll get to this later so you guys actually know what these functions do, but that's just in there for you so you guys know what functions to use. If you read something other than these characters, you print invalid input, this string right here, and then you just continue reading characters. Does that make sense to everybody? Cool. So like I said, you're going to implement this stack using an array. The maximum stack size will be 1,000 elements. If you ever get an operation that tries to violate the stack size, which basically means you try to pop an element off the stack and it's empty, or you try to push something onto it and it's full, you print out the message invalid stack size exiting, and then exit your program with the exit function. And then finally, once you reach the end of your input, and input's coming from standard in on this problem, you will print out the contents of the stack with the position of each element on the stack. So right here, we read in all these numbers, we do some operations on them, and then there's 1 element left on the stack, so we say position 0 has 6 in it. Down here, we run it and we just put 2 elements onto the stack, and then we end the input, and we see there's 2 elements, so we print from the top down. So we have position 1 is 4, position 0 is 3. Does this problem make sense to everybody? Great. I'm sure there'll be plenty of questions on it, but yeah. All right. Yeah.
After like today's lecture, do you think we'll have covered everything for the assignment?
Probably after tomorrow's lecture. Yeah. Yeah. I don't think we'll get to talking about like reading in characters or anything today.
Okay.
It's fairly straightforward, but hopefully we'll definitely talk about that tomorrow, and then hopefully get to arrays tomorrow as well. So yeah. Great. But you guys are definitely, you have everything that you need to work on this first problem though. So if you want to get started on it, yeah, start working on that. Cool. Any other questions about that? All right. Just a quick review. The main thing we talked about yesterday were bash control structures. Does anybody remember the two things we talked about? The two control structures? What was that? A for loop. What was the other one?
If statement.
If statement, exactly. How did the for loop work? Does anybody remember?
For do done.
Yeah, so you would say for some variable name in, and then what comes after in? A list, right? It's a list of elements. And then you say, so you say for some variable name in a list, do, then you have the body of your for loop, and then you say done. So the key part is that the for loop is going to iterate through each element in that list, and for each iteration, that variable is going to take whatever current item it's at in that list as its contents. What about the if statement? How did that work? How did, as far as like evaluating the control statement, how did that work? Does anybody remember? Yeah.
Is it if some command, then command, then,
Exactly, yeah, so that's the structure of it. You have if, and then you have the square brackets. That's where your control statement is. Then you say then, and then you say phi at the end of it. But as far as the actual control statement, the logical statement within the brackets, does anybody remember what that corresponded to in Unix? The test command, right? So there's a command called test that we looked at briefly. And if we go to Lectura, we can just look at the man page for it. There's this command called test, and this is how it evaluates these logical statements in the control structure. So there's all of these. This man page, if you ever get stuck on how to use it, is great because it just tells you exactly how to compare different things within those logical statements. So, yeah. So that's how you would use it. Great. So yeah. So for the to-do.sh problem, you're definitely gonna need to use like a for loop and some if statements. Yeah. So you'll definitely be using both of those. So it's good that we talked about it. Just know that you'll have to use those in your solution. Yeah.
are there like cases?
I think there is. I've never used it, but there probably is. I believe there is. But I think there's like 4 cases you'll need to handle for the to-do. So, I mean, you could just, if you want to, you could look into the case structure and use that, or you could just use if else ifs, you know. So, yeah. Great. Any other questions? All right, we'll just jump in back to where we left off yesterday then. So we finished yesterday by talking about I kind of introduced C, how it was made and everything, and talked about some of the good and bad aspects of it. And then this slide right here, we just started to compare C to Java. So we had this Java program called iota.java, and what it does is it just reads in, or it takes one command line argument that's an integer, and then it prints out integers from 1 to n, where n is whatever integer it read in. So we have this C program that's identical to this Java one we have right next to it, and we can see, you know, it looks fairly similar. Some of the syntax is different, but at the core it's really just, you know, grabbing a command line argument like it does right here. Here it's casting that string to an integer. This function's casting that string to an integer. And then we have 2 for loops which actually have the same exact syntax. And then we're just printing the integers out as we go along. So they're pretty similar. Up here we have some include statements, which anybody that remembers, what did those include statements correspond to in Java? what are they kind of like? Yeah, they're kind of like imports in Java. Yeah, so it's pretty similar. The C program above, right, is complete and compilable. Just a little bit of information. By convention, C source files have the suffix .c. So as you saw, like on the assignment spec, all of your programs will end with .c. C functions can be distributed among files as the developer sees fit. There are no Java-like file naming requirements. There are no classes in C like there is in Java. All executable code is held in functions, and a way you can think about it compared to Java is it's kind of like just one Java class file where all the code is contained in methods within that class. So we can use the GCC command to compile a C program, and this is the command for now that we will use to compile all of our C programs. So what I would recommend, I don't know if any of you have done this, but I had that little tutorial, you could say, about setting up your bash RC. I would recommend just putting this command into your bash RC, so that way you can say GCC and you'll have all these options already attached to it and you won't have to type them out. So let's use that GCC alias to compile iota.c. When compilation is complete, if no name is specified, GCC creates an executable called a.out. So if you don't specify what you want that executable to be called, it'll just automatically make an executable called a.out. And a.out stands for assembly output, or assembler output. So here we compile our program, and then we just print out what it is, and we can see here that it automatically makes it an executable file for everybody. And yeah, so then we say file a.out, and this just gives us more information about what exactly it is. It tells us it's an ELF 64-bit executable file. It was dynamically linked with shared libraries, and it's for GNU/Linux operating system. And then it gives us the hash code for the file, things like that. So we can go ahead and run it. We just run it the same exact way as we would a Java program, and it just again prints out all the integers from 1 to whatever number we give it. So yeah, so just remember that GCC is the command we'll be using to compile. By default, GCC creates a file called a.out. Yeah. So GCC's -o option can be used to specify a name for the executable if we don't want it to be called a.out. So here we are compiling that C file and we're calling it iota rather than a.out. And we can see that it created this file instead of a.out now. We can run it in the same exact way that we did the other one as well. So unlike Java class files or Python files, .py files, which could be run by any up-to-date Java virtual machine or Python interpreter, executables like the one we created up here called iota they're usually not portable between operating systems. Does anybody know why that would be? Well, when we're compiling a C program, it's turning it into binary code, right? It's making a binary executable. If I take a binary executable and run it on my computer has a very specific processor in it, right? That takes certain instructions that it understands. If I take my executable that has some set of binary code that my computer understands and I put it on somebody else's, if it's not the same processor, if it's not made by the same manufacturer, it might not understand those same instructions. So typically, just passing around an executable, it might not work the same if you give it to somebody else, right? So that's an interesting point, that if you just have an executable that you're giving to somebody else, it might not work, versus having Java class files or Python file, it could work no matter what operating system you're on. So for instance, I tried iota on a Mac that my family had, and we run it and it says it cannot execute binary file. So it doesn't know what's going on. And this was compiled on Lectura. So yeah. So Bash has a built-in command called time that lets you see how long a program runs. So yesterday we talked about how, well, first of all, we can just run it right here and we see the kind of output it gives us. It tells us what the total time that we would have seen the program run for was, what the time it spent in program code was, and what the time it spent in kernel code was. And so I don't know if anybody remembers, but yesterday I mentioned how C, one of the benefits of C code is it's really fast because it can get, typically it's 80 to 90% as fast as a handwritten assembly program, which is really good. So right here in this slide, we're just going to go ahead and compare those two IOTA programs that we had and see what the time difference is. So first we run this Java program, and we're using this built-in command I talked about called time, and we just say time, whatever command we want to run and see how long it takes, and it will give us a report. So right here we run it, I direct the output of the program into this file called X. Here I'm running the C program version, direct the output of the file into this output of this program into a file called Y. Here I diff the two files just to show that they're producing the same thing. And then over here we have the results from them running. So we can see that the C program is a lot faster, right? It spends almost no time in the system. The user time is barely any. You know, it just seems a lot faster, right? Yeah.
So you said that C is like 80 to 90% as fast as assembly. Like, what is Java?
That's a great question.
I don't know if there's like a direct translation.
I don't know what the direct translation is, but you can think about it because Java runs, it's not just executing binary code, right? There's a whole Java virtual machine that's has to start up and run, and then it actually takes your program and runs it within that virtual machine. So, you know, that's like one of the reasons why Java is a lot more secure than C, why Java, we talked about yesterday, C has a lot of issues as far as memory management and how that falls on the programmer rather than the system. So in the Java virtual machine, all those things are handled for you, but at the same time, that's kind of where the speed cost comes from. I don't know the exact translation, but you can see up here that it's like, here it's, you know, 10 times the amount, 15 times the amount of time in the user code. It's a lot more in the system code. In the end, it's not that much different when the user's actually running it, but, you know, it does end up being faster in C, and I don't know the direct translation. Yeah, so C is a lot faster than Java. So another big difference between these two languages is error handling. Like I said, the Java virtual machine can do a lot of these things for us when we're running Java programs, like it knows how large arrays are, and if we ever try to access outside the bounds of an array, it'll report this to us. So right here we're running our Java IOTA program, and notice that we don't give it a command line argument. However, in our program we just said, we were just accessing that command line argument array, just saying give us that first element out of there. So this should be an error, right? Because the array won't have that element in there. So Java tells us all this information like, hey, you had an array index out of bounds exception, this was the line in your program that it occurred at. However, if we do the same thing with our C program, we don't give it a command line argument, this is all the information we get. So it doesn't really tell us that much, right? Thankfully, when we get a segmentation fault like this, it says core dumped right here, and it produces a file in the directory that you're running it called a core file. And what a core file is essentially a snapshot of what your address space of the process looked like when the program failed. So it's basically just a bunch of ones and zeros or hexadecimal, depending on how you read it, and it's just what the memory looked like when your program failed. So if you want to, you can add ulimit-c 1000 or 1 million to your .bashrc to enable core dumps. And the name core comes from the term core dump, which in the early days was a word-by-word printed listing of memory contents used for debugging. And a core is a tiny ferrite ring that magnetically stores 1 bit. And you can Google these images of them, and this is actually what it is like on a circuit board. But so essentially we have these, when we get an error in C, it produces these core files. And we could look through it manually like it says they had to do in the early days, where it created a word-by-word printed listing of it. However, people have created tools that allow us to look through it more easily. So one of the most useful tools when you're debugging C code is a tool called GDB, which is the GNU debugger. Given an executable and a core file generated, when running it, GDB can be used to conduct a post-mortem analysis. So essentially what it will do is it will take that executable you give it that's associated with the core file that was generated. It'll run that executable and find where something went wrong in your core file. So here's just an example of starting up GDB. A bunch of stuff gets printed out up here. Here it says reading symbols from IOTA, so this is just getting all the information out of the executable. And then it says the program terminated with the signal SIGSEG-V, which stands for a segmentation fault. And then it gives us a bunch of information that doesn't mean too much to us right now, but eventually this will be really helpful because it tells us a lot about what's going on in the program, and rather than just having segmentation fault core dumped, you guys will actually be able to open up your buggy programs in GDB and be able to pinpoint exactly where the error is happening at. So we'll talk about this a lot more later because it's really useful, but just want to make you guys aware of that. And you can see down here it kind of tells you these would be the lines that you're actually interested in because it tells you where the bug is in your code, and these are all just library calls and things like that. So what exactly is different from C compared to Java? There's some syntactic differences. However, a lot of the basic syntax is similar when it comes to like assignment, conditionals, loops, and things like that. The biggest differences in C compared to Java are conceptual. C is procedural rather than object-oriented, so there's no notion of classes and inheritance hierarchies and things like that. It's all just, in the C program, it just starts from main and it's just straight line code from there. C is much closer to the machine. However, this means that debugging sometimes requires thorough understanding of what's actually going on at the machine level. In C, we have explicit dynamic memory management. We'll have functions such as malloc and free, which we'll talk about later. And dynamic memory management can be really useful, but it can also be a pain at the same time. In C, we have pointers, whereas in Java, we just have references and we can't actually determine what a variable is pointing to. In C, there's no garbage collection, so if we ever allocate some memory that we're going to use, we have to handle that ourselves. There's no concept in C that will handle deallocating that memory for us. There's no array boundary protection in C. You have much more control in C as far as what's going on at the machine level. And this means you can write faster programs. And it also means code can be hard to debug and security vulnerabilities are much more likely. C is generally compiled to machine code, which we kind of touched on earlier, while Java programs require Java machines, the JVM, to be installed. Yeah. So that's kind of the introduction to C. Hopefully that kind of sets the stage for everybody to see where we're going. And next we'll talk about the compilation of a C program. So in every program language, there's two key facets. There's syntax and there's semantics. So can anybody tell me what syntax is? Does anybody know? No? Well, syntax specifies the sequences of symbols that are valid programs in the language. So syntax is what tells us, we can declare a variable by saying int x semicolon, and it tells us that we can't declare an int by saying x int semicolon, right? It's the set of rules that tells us what sequence of symbols is valid in our language. What about semantics? Anybody want to take a stab at that? Kind of. That's more syntax. Syntax is more like the grammar of a language because that's telling us what sequence of the symbols our language is made out of is valid. Semantics is telling us, okay, we may have something that's syntactically valid, but is this actually allowed in the current environment we're looking in? So it specifies the meaning of a sequence of symbols. So what meaning does this sequence actually have? So consider this expression from our Java program. We have integer.parseInt, and we're passing in an element from our argument array. Is this expression syntactically valid? If I put this in a Java program, would it compile?
That little semicolon.
Oh, imagine there's a semicolon there. Well, yeah, it is syntactically valid, right? Because as far as I can tell, besides a semicolon, there's nothing that violates what's required in the Java syntax, right? So yes, it is. How is validity determined? So typically, it's determined programmatically by the parser, which is a component of a compiler that you use to compile your program. And within a parser, you mentioned a grammar earlier. Every language has a grammar that defines their syntax, and a parser essentially checks, is this input program that I'm given following my grammar? What's required for this expression above to be semantically valid? So again, semantics specifies the meaning of a sequence of symbols. So does this have a valid meaning? What would have to be true for this to actually work?
You have an argument.
Say it again?
You have an argument.
What exactly do you mean by that?
Like arg0 is actually something.
Right, so first, you have a great point. Args would actually have to be an array, right? Otherwise, this array access right here wouldn't work, right? What else?
First element, args, should be
Okay, that's not so that's not necessarily semantics because that goes into, that's determined by how the program is run, right? But in order for us to actually access something like this, args just has to be an array in the first place, right? How about this function or this method parseInt? What has to be true about this? Well, this method would actually have to exist, right? So this integer class would actually have to have a method called parseInt for it to be semantically valid, right? Another thing would be this method would actually, it would have to take one string, right? It couldn't take more arguments or less arguments. So args must be an array. The subscript of args must be an integer. The class integer must have a static public method named parseInt that accepts one argument whose type must be compatible with the type of args. So, these are some things that are different from syntax because you could have any valid statement within here, right? Maybe this 0 in here is a variable, but for it to be semantically correct, that variable would actually have to be an integer. So what's the type of arg0? It's a string, so that means that this is semantically correct, this expression, because it follows all of these things. So when a Java program is being compiled, what is the name of the file that the Java compiler would consult to determine whether a call, such as rectangle r equals new rectangle 34, is valid? So how does the compiler know that this is a valid line semantically? You would have to check the rectangle class file, right? Because that's where this method would exist. So when we run this, Javac will have to read integer.class to see if an appropriate method exists. So that's just to kind of set the stage so we understand how compilation is working in Java and how that will translate over to C. So first, let's check the size of our iota.c program and compile it again. So we have our iota program, and we see that there's 9 lines in it. There's 26 words, 164 bytes. And then we compile it again to an executable called iota. Let's walk through what's actually happening when we run GCC. So the first step when we run our compiler to compile this program is the C preprocessor is run to include files, expand macros, and more. So we can look at what's happening at this step by using the -e option with GCC. So this essentially means run our program through the preprocessor to include files, to expand macros, and all this other stuff, and it will produce that preprocessed file. So we're compiling it and we're capturing it into this file called iota preprocess.c, and we notice that this was the original word count for the file, and the file has grown a lot. So when we run it through the preprocessor, it's sticking all this other code and everything into there, so the file's actually growing. So remember how we talked about how C is just one straight line code file with a bunch of methods in it. That's what this is actually doing. It's putting function definitions and things like that into the file, and it's creating a new file through this preprocessing process. So the next step in compilation is this preprocessed C code right here is compiled to an assembly code file with a .s extension. So we can create an assembly file by using the -S option with GCC, and we give it our preprocessed file, and we see that our size has been reduced a little bit because now we're just in assembly code rather than this kind of lengthy syntactic C code. The next step is the portable GNU assembler, which is AS, the command if you want to actually run it. We run that on this assembly code that we generated down here. So we run the assembler, and what this does is it produces an object file with the suffix .o. And like it says right here, despite the name, there is no relation between object-oriented programming and object files. So we run it with some options up here. We say to call a new file, iota preprocess.o. Here we're specifying that we're running on a 64-bit system. And we've created this .o file, and we see that it's a ELF 64-bit relocatable file. Here we can say we see it works on 32-bit or 64-bit system. And then finally, for this step, we can use nm to show what symbols are present in an object file. So if we run this on our preprocessed object file, it'll show us what functions are used. So here, it's printing out A2I, main, and printf. And these are all the symbols that are used within our program. If you remember, what our program did was it had its main function, it called A2I on one of those command line arguments, and then we called printf. So these are all of those symbols that we use. So these U's indicate that A2I and printf are referenced, but they're not defined in our object file. So we're using them, we include those header files so we can actually use these functions, and we reference them, but they're actually not defined. Like the actual code for those functions aren't in this object file right here. Then we have our main function, and this line of zeros right before it, this is telling us what address it starts at within this file, so we can see it's a bunch of zeros. So our main function is the first thing within this file. Cool, so it's created this object file, and this has all of our code that we're actually running inside of it. It's not going to the next slide. Oh, disconnected from the internet.
Still recording.
Yeah, it's still recording. So it's not letting me present it because apparently I disconnected from the internet. I guess we'll just do it like this then. So the fourth step in this C compilation process is we link our object files together. And this is where the actual creation of the executable comes from. And so notice that we use the GNU linker, which is called LD. And again, what this will do is it will combine any object files that we're using together and create this executable. So right here we can just run this by saying ld-o iota, so that's the executable file that we want to create, and then we're saying iota-preprocess.o, that's the object file that we want to use, and we have this -lc option. So what's actually happening is we're running a GCC command, but it's actually just disguised as LD. So if you do gcc-v, you can see all the commands and things it's doing to the file if you'd like. So at this point when we run this, I said before on that previous slide we saw that we were using A2I and the printf functions, but they weren't defined in that file. So there's actually an object file that contains all of the C library functions in it. So what happens in this step is every time you run through the compiler, your program will automatically be linked with that library object file. So all of those things, all of those library functions that you're using will automatically be linked in and you can use them. So we run it and we see that finally after this fourth step we've actually created an executable file that we can use and run. So the high altitude view of the steps performed by GCC is first we pre-process the C source code to include any files we have, expand macros, and anything else that maybe needs to be done in there. We compile the pre-processed code into an assembly file, which is machine instructions. We then assemble this assembly code into an object file, and then the final step is we link all these object files together and some library code into an executable. So again, try using GCC's -v option if you'd like to see all the steps that are happening there. And the steps that are shown right there date all the way back to the early days of C, so this whole process that it walks through has been going on for a really long time. They really haven't changed it because it just works well. And finally, GCC is just an implementation of a C compiler. There's other C compilers out there. One of them is called Clang. I'm sure there's other ones, but those are really two of the big ones. There's the GNU compiler, and they might do things completely differently. So this is how GCC walks through and compiles code, but other compilers might do it differently. The C11 standard, which is the standard for the C programming language, doesn't dictate how you need to compile the code. It just talks about the semantics and how it actually works. All right, so that's how the compilation process works. So let's go ahead and take a 5-minute break. I'll try and figure out the internet, and yeah, then we'll talk about the preprocessor.
I can't get on the Wi-Fi.
Really? That sucks.
Set up a hotspot on your phone.
I could. I'm too lazy to do that. That's cool. That's really weird. All right, let's start talking again. So now we're going to talk about the preprocessor, which we briefly talked about. Let me just do this real quick. Yeah, I did a hotspot on my phone. So the preprocessor, let's just open it up in here. I need to figure out how to actually present it. Look at that. Alright. So one of the fundamentals of C is the idea of preprocessing. And we kind of talked about this a little bit because I mentioned header files, which we can see up here are these .h files. So one of the fundamentals of C is the idea of preprocessing. Before a C program is actually compiled, the compiler runs through and performs textual substitutions on lines starting with a £. And these lines are called preprocessor directives, and it essentially tells the preprocessor to stop and look at that line and do some sort of substitution while the preprocessor is running through the file. So iota.c, this program we've been working with, has two such directives right at the start. We have #include standard io.h and #include standard library.h. So the line #include standard io.h directs the preprocessor to temporarily suspend reading lines from the current source file. And what it does is it goes and opens up that file that it's directed to, and it starts to read those lines in the header file, and it substitutes them into the current source file that it was reading. So when all the lines have been read from standard io.h, processing of the original source file continues. So in effect, the #include causes the text of standard io.h to be inserted into the current stream of source code, just as if it had been pasted in with an editor. So it kind of expands out to be whatever is actually contained within that file. And I think this is the best way of putting it. It's just like pasting that code into your original source code with an editor. So the use of angle brackets in a preprocessor directive indicates that standard io.h is a well-known file that's found in an implementation defined directory, which on most Unix-like operating systems is in /user/include. So within these header files, they can have their own include directives. So we can go ahead and look inside of standard io.h, and we see that it has its own include directives, such as this one, libio.h, and these other ones right here. So as we talked about earlier, GCC's -e option sends the preprocessor output to standard output. So let's see how many lines are generated by preprocessing iota.c. So we run our iota program through the preprocessor with the -e option, and if you recall, our program was only 10 lines long. After we've run it through the preprocessor, it becomes almost 1900 lines long. So all these things are being pulled out of these other files that are being included and basically pasted into our small little program. What happens if we remove our include directives? So here we're dealing with the same program, and I just commented out with the // symbol. I comment out our include directives right here, and then we try compiling it again. And so what happens is it gives us some warnings. Right here we see iota.c in function main. There's an implicit declaration of the function a to I, and there's some more information at the end that I cut off. Implicit declaration of function printf. Incompatible implicit declaration of built-in function printf. So this is just getting mad at us that we're trying to use a function that it hasn't seen a definition for. It doesn't care if it's actually seen the body of the function. It just wants to know what that function definition looks like so it could determine if we're actually using that function and calling it correctly with the correct number of arguments. So we discussed earlier how Java uses the class files to check semantics, to check if those method calls were correct and if it was using the right type of variable and everything. In C, we can kind of use these includes of header files to specify function signatures. So like as I was just saying, the compiler can use those function signatures to check the semantics of our program. So let's uncomment our includes files and see where a to I and printf appear in our preprocessor output. So right here, we're again just putting our program through the preprocessor, and then we're searching for the terms a to I and printf with grep right afterwards. we're using a type of grep called egrep, which allows for regular expressions, and this is just saying find instances of A2I or printf. So here we see there's a definition extern int printf, and then there's a bunch of arguments it takes, and there's also extern int A2I, and there's one argument that it takes. And then down below it, we also captured these are where these functions are actually called. So when we run this, again, this is our output, and we'll later understand what these two prototypes right here mean, but what these two essentially mean is that printf takes one or more arguments, and that's what that ... means. And the first one is a string, that's what this constant char star means. A2I takes a single argument, which is a string, that's what this char star means again, and both of them return an integer, as we can see from the function signature at the start. So the preprocessor is putting these function signatures into our code, so that way when the compiler runs through it, it can actually find these function definitions and say, hey, is he calling printf correctly down when he actually uses the function? Is he using A2I correctly when he uses the function? Yeah?
Do you need a different print method to print a string?
No, so we'll talk about printf tomorrow, but it's essentially what it does is you give it a string of characters, just in quotes, and how strings work in C is really weird in general. We're going to spend a lot of time talking about that, but if you want, you can just give it some string in quotes to print out, and then if you, for instance, wanted to print an integer, you say %d, and then afterwards you would specify what integer you want to print out. And that's where that varying number of arguments comes from. Because if I wanted to print 3 integers, I'd have 3 %d's in here, and then I need to specify the 3 integers I want to print afterwards. So yeah, so one use for the includes is to specify function prototypes that the compiler can use to check the semantics of function calls. Note that we might need to include a file with thousands of prototypes just so the C compiler can check a single function call. This Java program prints out the min and max int values, and it's called int_min_max.java. In all these programs that we're looking at, I mentioned it yesterday, there's that folder called lecture in our class directory, and all these programs will be in there. So right here we have a Java program, and it's just printing out the maximum integer value and the minimum integer value. And we can see what we do is we have our integer class, we're just accessing the object variable min_value and the other object variable max_value, and then we're printing it out. And as I was just saying, we're actually using a similar function call as printf down here, but we have these %d's, then this integer corresponds to that one, and the second one corresponds to the second %d. Here's the C counterpart called int_min_max.c. Right here, we have our main method, we have our printf, where we're printing out the minimum and maximum values. So what's new in this C program that we haven't seen yet? Yeah?
Well, in Java, when you have to call an integer class to get it, but this seems like in C it's just its own variable or constant, I guess.
Right. Right here, we're just using these variable names. That's what it appears to be, called int_min and int_max, right? And those are going to give us whatever the lowest and highest value for an integer is. Where do you think that's coming from? Yeah. Exactly. So you pointed out that there's this file called limits.h that we're including, and that's exactly where these values are coming from. So another use for this is for these .h header files is to include values that we want to have consistent throughout programs. So again, right here we're just going to look at that limits.h header file, and we search for int_m, because those are the values we're using right here. We search for that within this file, and it comes up and we see that int min first is defined as the negative of int max minus 1. We see that the int max is defined as this really big number, and then we have uint max is defined as an even bigger number. So these are defining values for us that we can use throughout our programs as long as we include this limits.h header file. Kind of a side note, does anybody know what uint max is as opposed to int max? Does anybody know the difference between a normal integer and an unsigned integer? Okay, good. Good that we brought this up then. So, in normal integer, it can be either a negative number or a positive number, right? So that's why we have this right here. Because notice we have some integer max, and we have negative integer max minus 1. An unsigned integer can never be negative. So notice how this is about double the size of this number, right? So all of those values that are below 0, an unsigned integer can never represent those, but then it can also be double the size of a normal integer. So notice how it's about double what the normal integer's max is. Alright, so a normal integer can also be negative. So why do we have negative int max minus 1? Why is it not just negative int max? Yeah.
I forgot the name, but it's like when it gets to the maximum, it goes to the last possible negative number.
Maybe, I'm not sure exactly what you're talking about.
I forgot the name. It's when that integer gets to the limit of the maximum
Oh, it
number,
overflows.
If you add more, it's gonna go to that like
Right.
most negative number.
Yeah, so if you go beyond the max size of an integer, it'll overflow and it will go down to a negative number. But that's not exactly what's going on here. So what's going on here is we have all of these positive numbers we can represent, right? But we also got to represent 0 somehow. So 0 would just be where all the bits in the number are zeros, right? But now that we have that representation of 0, either at the positive end or at the negative end, there's got to be one less number, right? There's not going to be an equal amount of numbers anymore. So they've just decided that the standard is that it always will be this one less negative number than there is positive numbers, right? So that's where that comes from.
So that minus 1 accounts for the 0.
Right, exactly. Does that make sense to everybody? Cool. Alright, so here we're using limits.h again. So let's see what the preprocessor is doing to our program when we have these defined numbers and we run it through the preprocessor. So right here, we're running it through our preprocessor, and we grab the last 5 lines of the file that was produced. That's what this tail command is doing. Because if you remember, that file was like 2,000 lines long. So the last 5 lines, we have some other defines and things that it's doing right here, but then we have our actual main method. And notice, before we had int min right here, and we had int max right here. This has been substituted in to be int max minus 1, and this has been substituted in to be int max, right? It's no longer those variable names, but it's been substituted in to be actual numbers. And it's literally, when we first talked about the preprocessor, we talked about how it's a textual substitution. It's literally taking that exact thing that we had before and putting it directly in. Notice how if you remember, this has int max in it, right? Int min has int max in it. So when the preprocessor is running through the program to substitute things in, if it substitutes int min here, it will then have to substitute int max, right? So there might have to be multiple passes over the file to make sure everything's been substituted in correctly. And finally, just so we can start using this terminology, these defined numbers are said to be macros. They expand into the text that replaces an identifier. So in this example, we're defining the text we're defining with a macro is a number, but we can define a macro to be any string, really. And that's where this next slide comes in, because we can also have macros that have parameters. So here's a macro that will help us explore C. So I've created a header file that I just called iprint.h, and I put my own macro that I wrote inside of it. So here we see it says pound define iprint, then there's parentheses e, and we have printf, the pound sign e, we have some string right here, and then we have e again. So you guys can see what it's doing down at the bottom, but just looking at this right here, what do you think this would do if I called iprint with some parameter? So this is kind of like a function, right? I can pass some parameter into this macro, and whatever I pass in as e, wherever an e appears over here, that will be substituted in. So going down here to the example real quick, we have this file called iprint1.c, and in it we have we include standard IO, and we include this iprint.h file that I have up here. So notice how I call iprint with 5 plus 7 times 3, a plus 25, and argc. I compile the program and I run it over here, and we get 5 plus 7 times 3 is equal to 26. We get a plus 25 is equal to 90. Argc is equal to 1. So what this is doing, and it's going off, the slide's going off the bottom of the screen, but what this is doing is it's substituting these terms we're giving it into this printf call, right? So when we have any call to iprint, it actually becomes a call to printf. So we have this iprint 3 plus 4 right here, and then what it does is it expands out to printf, and it substitutes 3 plus 4 in wherever there was an e. So we can see that this text 3 plus 4 has replaced e at the end of the expression. What's going on with the pound sign e? So this rule with the form pound sign, whatever the parameter was, says to insert the parameter at that point in the macro, but wrap it in quotes, making it a string literal. So if you notice, there's no quotes around e right here, but this 3 plus 4 has been substituted in with quotes around it. And then also, juxtaposed literals are considered to be a single string literal. So notice how there's this string with this string right next to it right here. Those are all considered to just be one string. You don't need to append them in any sort of way. So the end result is that iprint 3 plus 4 is equivalent to this printf call because we've defined this macro. Does that make sense? Great. Just back on the last slide real quick. I have this file up on our in that lecture folder I was talking about, which is at this path right here. And if we wanted to, notice how I include that file with quotes around iprint.h in the program. If you want to be able to do that in your programs with header files that you've created, you can use the -i option in your GCC command. And you could just even add this into your alias that you have if you wanted to. So I use -i and then I specify this path. And essentially what this is doing is it's telling GCC to look at the directory specified by that path for any header files when I'm compiling. So now notice how when I include it in my program, I have quotes around it rather than brackets. So if I put brackets around the file I want to include, that tells the preprocessor to look in the standard library header files to see if it exists there. If I have quotes around it, that's telling GCC to look along one of these paths, and that's where it will exist. Or look in my current directory. Great. So we've seen the preprocessor use, sorry, was there a question?
I have one more question. So for that statement, if you didn't include the # before it, would it still get picked up in like compiling or runtime, or would it just not work at all if it wasn't in the preprocessor part?
So the preprocessor always occurs before the actual compilation. So yeah, it would run, and what would happen is these quotes wouldn't be surrounding the 3+4, right? So then once it actually gets to compilation, there'd be an error. So, yeah, good question. So we've seen the preprocessor used for the including of files and macro replacement. It does more, including conditional compilation, which we'll get to later, and it's very useful when you're dealing with large C programs. Along with the function prototypes and macros, header files contain structs, typedefs, constant values, and other things that we'll be learning about. There are tons of header files on Lectura. Just looking in /user include, there's 3,287, and then right here, this is showing how many of them have includes, how many of those header files have includes within them, and it's a lot, right? So the preprocessor is very powerful, but it has many pitfalls too. We'll learn about it more soon, but that's all we need for now. So are there any questions about anything we just talked about? Cool. We'll just go through this topic real quickly. This is talking about bits. I'm not 100% sure how many are familiar with the concept of a bit, but we'll just talk about it real quickly. So, a bit is the basic and physical unit of information in computing and digital communication. A binary digit can only have one of two values and may therefore be physically implemented with a two-state device. So the term bit is a portmanteau of binary digit, and so essentially what that means is bit is binary digit combined. So it's essentially telling us it's 0 or 1, right? It has two states. So there's the concept of binary values, which are a sequence of binary digits, right? So with n bits in order, we can represent 2 to the n items. So if we have 1 bit, there's only 2 unique values that we can represent, right? Because that 1 bit either has the state of being turned on or off, right? A 1 or a 0. Real quickly, how many people know like binary and converting from binary and stuff like that? Okay, so a lot of like iffy. Awesome. So if we have 2 bits, we can represent 4 unique things, right? I really wish I had a way to type them. I guess I do. So if we have 4 bits, 2 bits, we can represent 4 unique things, right? So we can either have 0, 0, we could have 0, 1, we could have 1, 0, or we could have 1, 1, right? So there's 4 different things we could represent with 2 bits. If we had 3 bits, how many things could we represent? 8, right? Because as it says on the slide back here, we can represent 2 to the n items with n bits. So 2 to the power 3 is 8. And those different ways we could represent that would be 0, 0, 0, 0, 0, 1, 0, 1, 0, and going on and on with all the different combinations. So again, we can see how this is really useful for storage in a computer. Because having 1 bit means I can represent 2 things, but if I just expanded that out to say 16 bits, I can now represent 65,000 things. If I expand that out to 32 bits, I can represent 4 billion things now, right? So this is the way data is stored in a computer, right? It's binary digits laid out on a disk or in whatever kind of memory you're using. Oh, I'm all the way back at the beginning. Cool. It's not what I wanted. So we kind of just talked about this, but what's the largest number 3 bits can hold? And it's up on, well, no, it's not. The answer is kind of up on the screen because the largest number 3 bits can hold depends on the representation. So here we have a simple representation where we have, okay, if all 3 bits are 0, that integer it's representing is 0. If all 3 bits are 1s, that number it represents is 7, right? Here we have the 2's complement representation. So here we say, you know, if all 3 bits are 0, that represents 0. However, if all 3 bits are 1, that represents -1. If we have 0, 1, 1, that represents 3. And if we have 1, 0, 0, that represents -4. So this is how integers are represented. They use 2's complement. So I think I made a mistake earlier. I said that the negative integers go 1 less than the positive. I believe it's the other way around. Negative integers go 1 higher than the positive integers. But you can see right here, this representation of binary numbers, we just say if the binary number starts with a 1, if the bit farthest to the left is a 1, that's going to be a negative number. And then we use the rest of the bits to actually determine what number that will be, right? So here we have 0, 0, 0. We just say that represents 0. 0, 0, 1, it starts with a 0, so we know that's going to be positive. And then we look at the last 2 digits, and we say that represents a 1. Here it's the other way around. It starts with a 1, and then we say 1, 1 represents -1. So you don't need to understand the specifics of this, but this is just illustrating that there's different things that these can represent. So there's not one predefined way, there's not one maximum number 3 bits can represent, right? So finally, computers are often characterized as being n-bit machines. So here's a list of a bunch of different machines. The PDP-11, this is the machine Unix was first developed on. Pentium with x86-64, that's a lot of the processors that are on laptops nowadays. These are 64 bits, the PDP-11 was only 16 bits. We see this was only a 4-bit machine. And what it means when you have an n-bit machine, and this is a super generalization, but it essentially means an n-bit machine tends to work more efficiently with data in n-bit words. So it's really good at dealing with data n bits at a time. So an example is a 32-bit machine may store 32 bits of data more quickly than it would store 16 bits. And again, this is kind of a super generalization, but the reason that you have a 64-bit machine versus a 32-bit machine is it works with that size of data more efficiently. And the reason that you would rather have a 64-bit machine rather than 32-bit is because, as we saw on this slide, we can represent this many different things with 64 bits. So if your processor is really good at handling 64-bit words or chunks of data, then you would rather deal with that. So a bit, it's just important to understand the concept of a bit and how this is the foundation of how data is stored on a computer. We will be dealing with addresses and data represented in binary or hexadecimal a lot throughout this course. Make sure that you just kind of have the idea of what a bit is and how we can translate it to an actual number down. So tomorrow we'll start talking about like actually coding in C. We'll start talking about, you know, reading in input, printing out, things like that. Hopefully we'll get to arrays. But yeah, you should be, after tomorrow's lecture, you should be pretty good to go on the assignment. So see you guys tomorrow.